Hello, my name is Yoon-Seok Han from ADAS Lab at Seoul National University. This time, I will discuss about the reasoning and planning in LLM agents. At present, commercially deployed LLMs are known to handle complex tasks such as logical puzzles, mathematical problems, and code generation. These tasks typically require understanding the structural patterns of a problem and combining those patterns to arrive at a solution. For example, in ArcAGI2, multiple input-output grids for a given task are provided as few-shot examples, and the goal is to predict the correct output for a test input grid. As illustrated in the slide, this involves interpreting color segments and topological diagrams divided by blue lines, identifying the diagram that is topologically equivalent and applying the corresponding color. Similarly, AMI 2025 and LiveCodeBench are well-known benchmarks in mathematical problem solving and code generation, respectively. Solving these challenges demands interpretive and reasoning abilities akin to those possessed in humans. The commonality across these tasks is that solving them requires a step-by-step thinking process. First, interpreting the problems, then considering possible solution approach, and finally, verifying whether the chosen method is correct. Likewise, when an LLM is present with a problem, it demonstrates reasoning capability by breaking the problem down into sub-problems, addressing each sub-problem step by step, and ultimately arriving at a final answer. This is distinct from simply producing an answer immediately. Rather, the model exhibits its reasoning ability by explicitly showing how it reached to the solution. Early research on eliciting reasonings in LLMs began with prompting techniques. Instead of providing few-shot examples that only include the final answer, researchers structured the examples to show the step-by-step solution process leading to the final answer. This approach was found to unlock the reasoning abilities of LLMs. As a result, when chain-of-thought prompting was applied, where the solution process was explicitly demonstrated, models not only produced step-by-step solution path, but also achieved higher accuracy compared to prompting with final answers alone. Subsequently, it was reported that even without constructing few-shot examples, simply providing a cue such as "let's think step by step" is sufficient to elicit reasoning from LLMs. Remarkably, this approach was shown to achieve increased accuracy comparable to that of few-shot chain-of-thought prompting. As demonstrated by the previous findings, LLMs can be guided to elicit reasoning by producing chain-of-thought outputs. Naturally, this led to the next line of research, which explored ways to further enhance reasoning. The first approach is self-consistency, a decoding strategy in which multiple reasoning chains are generated during the decoding stage, and the most consistent answer among them is selected. Compared to the conventional method of sampling a single reasoning chain to obtain the answer, self-consistency has been introduced as a representative technique that achieves significantly higher accuracy. However, self-consistency has a critical limitation, since it selects the final answer based on fully decoded reasoning chains. An LLM, whose decision-making process proceeds left to right at a token level, cannot easily correct errors that occurs early in the chain. To address this, the tree of thoughts framework was introduced. Instead of generating an entire reasoning chain at once, it produced finer graded thought blocks and evaluates each block with a state evaluator to determine whether it could lead to the correct final answer, pruning unpromising paths along the way. In this framework, the sequence of thoughts branches into a tree structure, and the path to the final answer can be explored using strategies such as BFS or DFS. Let us take a concrete example to better understand the tree of thoughts. Consider the task known as the game of 24, where the goal is to determine whether four given numbers can be combined using basic arithmetic operations to produce the value 24. To solve this, an LLM first forms a thought block by combining certain numbers with an operation. As illustrated in the figure, when given the number 4, 9, 10, and 13, one possible thought block is performing the operation 4 plus 9 equals 13. At this point, the state evaluator examines whether the resulting 13, together with the remaining numbers 10 and 13, can still lead to 24. If it determines that the target cannot be reached, that branch is pruned. In this way, the model heuristically eliminates less promising branch and retains only those that with a higher potential to reach the correct answer. This process of exploring and pruning through branching possibilities is what defines the tree of thoughts approach. As shown in the previous studies, LLMs are capable of generating multiple thought steps, such as formulating a sequence of sub-goals to achieve a given objective. When these steps are integrated not merely as text but as action commands, the LLM can operate as an agent that interacts with its environment, leveraging tools or incorporating the outcomes of its reasoning. In this setting, reasoning naturally becomes equivalent to planning. At the foundation of today's agent framework lies the React framework. React generates thoughts and actions jointly, allowing the model to observe the outcomes of its action and then sequentially produce the next thought and action. When applied to tasks such as question answering and fact verification, this approach has been shown to outperform methods that rely solely on reasoning only or actions. Building on this idea, subsequent research has sought to enable more advanced forms of action. One notable example is HuggingGPT, which leverages the LLM as both a planner and a controller. In this framework, the LLM decomposed a user request into the necessary subtasks, selects appropriate AI model from Hugging Face to handle each subtask, and then execute those models. The outputs are collected and integrated, ultimately producing a response that fulfills the origin user request. More recently, Search R1 has been introduced, a model trained with reinforcement fine-tuning to call a search engine during the reasoning process. Search R1 learns to effectively invoke the search engine by using special tags such as search, and it is rewarded when the retrieved information leads to correct answers. Through this process, the model gradually acquires the ability to utilize the search engines strategically, enabling it to perform question answering with greater accuracy based on more reliable information. Research has also moved beyond simply generating plans, exploring how LLMs can create plans that lead to better actions. One such framework is reflection, in which an actor generates actions based on planning, while an evaluator assesses the utility of those actions and provides the actor with linguistic feedback to improve subsequent plans and actions. The verbal reinforcement cues produced in this process, along with the action trajectory so far, and stored as long-term memory experience and short-term memory trajectory, respectively. These serve as contextual signals that help the actor generate more effective actions. In a similar vein, the Plan and Act framework has been recently proposed, where a planner generates a high-level plan and an executor carries out lower-level steps based on it. After the executor performs an action, the planner observes the outcome and dynamically generates a new plan that reflects change in the environment. This approach has been shown to achieve superior performance on long-horizon tasks, such as those in the Web Arena benchmark. These diverse lines of research build upon the advanced capabilities of LLMs, which stems from their strong ability to understand long context and to generate extensive and informative outputs. It is particularly interesting that allocating greater computational budget at the test time for such advanced LLMs has been shown to lead to actual performance improvements. Accordingly, a new paradigm has emerged that seeks to scale not the training cost, such as data volume, parameter size, or training time, but rather the computational budget allocated at test time. Some studies even argue that scaling test time computation can be more efficient than scaling model parameters. The figure shown in the slide illustrates how, for tasks lower difficulty, increasing test time compute can yield greater benefits. For convenience, we can think of revision as analogous with the earlier reflection framework, and PRM search as similar in spirit to the tree of thought. In this comparison, the baseline is a model that is 14 times larger in parameter size, represented by stars, while the models that scale test time computation are represented by lines. The figure shows a clear trend. For easier problems, as test time compute increase, the performance lines consistently rise above the stars, depleting the advantage of allocating more computational at test time. As shown in the previous slide, increasing test time computation indeed leads to the performance gains, revealing the presence of a scaling law, a phenomenon also observed in OpenAI's O1. The fact that scaling laws apply here is particularly important, as it strongly suggests the potential to steady and predictable progress within this paradigm. Building on this paradigm, reasoning models that explicitly allocate additional computational budget at inference time has begun to emerge. One of the most influential is OpenAI's O1, first introduced as Strawberry in December 2024. Its debut sharpened the focus on test time scaling and sparked broad interest in reasoning-centric approaches. Shortly thereafter, in January 2025, DeepSeek AI announced a 685 billion parameter large-scale reasoning models and released it as open source, further accelerating progress in subsequent reasoning model deployment. Today, many commercial and open source LLMs explicitly allocate computational for reasoning capabilities, and some even allow users to control this by specifying modes or assigning a token budget for the reasoning. The development of reasoning models can be examined in detail through Hugging Face Open R1 project, which aims to reproduce DeepSeek R1. As noted in the DeepSeek R1 paper, instead of rewarding general response quality, the training focused solely on accuracy and format, leading the LLM to learn how to effectively utilize chain of thoughts. Looking briefly at the reward schema, we see that rewards are given when the model outputs in the correct format. For example, producing explicit reasoning steps with think and answer tags. In addition, an accuracy reward is applied when the completion matches the ground truth. When reinforcement learning is performed with such verifiable rewards, LLMs shows a clear trend. As training step increase, response length grows, and task accuracy improves accordingly. Recently, many open-source reasoning models such as QN3, Magistral, and Kimi K2 have adopted this RLVR paradigm. The fact that their outputs exhibit more explicit reasoning patterns and achieve higher accuracy on reasoning tasks suggests that RLVR is becoming the standard recipe for building reasoning models. Our methods for enhancing reasoning models, including RLVR, fall outside the scopes of today's seminar and will be addressed in future discussions. There is, of course, a clear trade-off in the fact that generating longer responses leads to longer chain of thought. While multiple studies have empirically demonstrated that longer reasoning sequences can indeed improve performance, the substantial computational overhead remains a persistent challenge. Moreover, several works have shown that much of the reasoning contents produced by LLMs is actually redundant, with only a subset contributing to performance gain. This phenomenon has come to be known as overthinking. To address the challenge of overthinking, the field of efficient reasoning has recently emerged, and it can be broadly categorized into three approaches. The first is the model-based approach, which designs the training pipeline with reasoning efficiency in mind. For example, reinforcement learning can be performed with a length reward, or supervised fine-tuning can be applied using chain of thought data of varying length. The second is reasoning output-based approach, which focuses on optimizing the reasoning process itself. This includes latent reasoning, where reasoning steps are compressed into latent representations rather than token-level outputs, as well as dynamic reasoning strategies during inference that resembles tree of thoughts. Finally, the third is the input prompt-based approach, where constraints related to output lengths are embedded directly in the prompt. For instance, instructing the model to respond within a given token budget. This also includes routing method, where different models are selected to answer based on the difficulty of the question. Let us now take a closer look at each approach by highlighting one concrete example for each. The first example under the model-based approach is DGRPO, which applies to LL fine-tuning with chain-of-thought data of varying length. In this method, the model first generates a control token that specifies the intended reasoning length, and it receives a reward when it successfully produces a reasoning process that matches the length indicated by the control token. Next, under the reasoning output-based approach, recently introduced work is InfinityThink. This method was proposed to address a key limitation of LLMs with restricted context length. When reasoning sequence becomes too long, the output risks being truncated. Here, efficiency is not about reducing computational budget, but rather about maximizing the use of limited context. Instead of outputting the full conclusion at each step, the model generates a summary of its reasoning, which is then pretended to the next iteration of reasoning. After several iterations, once the model reaches the final conclusion, the process terminates. In this way, InfinityThink effectively leverages limited context lengths to achieve maximum efficiency. Finally, let us look at the input prompt-based approach. Among these, routing has become a widely adopted technique, already familiar to many users of commercial LLM chatbot services. This idea is simple. Allocate a smaller computational budget for easy queries and larger budget for complex ones by routing the query to the most appropriate model before generating a response. In commercial LLMs, this technique was first popularized by Claude Sonnet 4. More recently, the ChatGPT 5 released in August introduced an integrated system combining GPT-5 Mini, GPT-5 Nano, and GPT-5, where selecting the auto option automatically routes the query to the suitable model based on its difficulty. Just eliciting and enhancing reasoning is crucial. Understanding reasoning mechanisms of models is equally important for guiding future progress and monitoring potential misaligned behavior. Accordingly, ongoing research has focused on whether the reasoning produced by a model truly reflects its internal computation. One prominent line of work is mechanistic interpretability, which analyze hidden states, individual neurons, or neuron circuits to examine whether LLMs genuinely follow a chain of thought. In the following, I will introduce some representative works for this area. First, there is a study that models chains of hidden states between sentences at a sentence level using a stochastic differential equation, enabling the prediction of the hidden states at the next step. The researchers demonstrated a high correlation between the predicted hidden states and the ground truth hidden states. Moreover, they observed that when the model exhibits misaligned behavior, the hidden states tends to fall into a distinct region, providing valuable insights into how such behaviors manifest. Next, there is a study that examined which neurons in the feed-forward networks of transformer blocks becomes activated when an LLM solves mathematical problems. The findings shows that distinct neurons were activated in correspondence with specific mathematical concepts such as logical connectors, additions, and subtractions. Furthermore, when these concept-related neurons were intentionally deactivated, the resulting performance degradation on related problems was significantly greater than when neurons were randomly deactivated. Finally, there is research focused on interpreting circuits where a collection of neurons. The key challenge in this area is polysymmetricity, where a single neuron is activated by multiple input features, making interpretation difficult. To address this, many studies employ sparse autoencoders. These modules are designed with the main objective of reconstructing the output of MLP layers. By using larger numbers of neurons than the original MLP and applying a strong L2 norm penalty on the weights, sparse autoencoders enforce sparsity in activations, thereby reducing polysymmetricity and making feature representations more interpretable. Using a sparse autoencoder, we can define the set of neurons activated by a given input token. The figure on the slide diagrams the circuit engaged by a query asking for the capital of the state that contains Dallas. This query requires two-step reasoning. First, inferring that Dallas is in Texas, and then producing Austin as the capital. Circuit analysis with the sparse autoencoder shows that the token capital and state activates related features, which in turn trigger a higher level, say a capital feature. The token Dallas activates features associated with Texas, and together with the say a capital feature, they activate the feature that drives the model to produce Austin, yielding the final answer. Let us look more closely at when the say a capital feature becomes activated. As shown in the figure, this feature is triggered in context where words related to the states, such as Massachusetts or California, appear immediately beforehand, followed by phrase containing the corresponding capitals, such as Boston or Sacramento. Examining the model's internal mechanisms in this way allow us to test whether the model is generally performing reasoning or merely predicting the most probable next token based on the training data. Interpreting these reasoning mechanisms is therefore a key approach to understanding how models reason. It also enables us to identify the directions in which reasoning should progress and to determine which components require adjustment when faulty reasoning occurs, ultimately playing a critical role in refining and advancing LLM reasoning. Thank you for listening to my Reasoning and Planning in LLM Agents seminar. If you have any questions, please feel free to reach out to me through email. Thank you.